Binomial coefficients solved problems. Problem 1. Find the binomial coefficient of the 10th term in the expansion of 2x plus 3y to the power 20. The rth term of the expansion of 2x plus 3y to the 20, which we can call t sub r, has the form 20 choose r times 2x to the power 20 minus r times 3y to the power r. And if we wish, we can write 20 choose r in this form. R ranges from 0 to 20 inclusive. The question asks us to find the binomial coefficient of the 10th term. The binomial coefficient is simply 20 choose r. So that is the only part of t sub r that we need to calculate. The rest of it is completely irrelevant for this question. Now we have to calculate the binomial coefficient of the 10th term in this expansion, but r ranges from 0 to 20, which means that the first term is labelled with r equals 0, and the 10th term is labelled with r equals 9. That means that we have to calculate 20 choose 9, which we can also write in this alternate bracket notation, 20 choose 9. The easiest way to calculate 20C9 is to use a calculator. On this Casio calculator pictured here, there is a button labelled NCR, which is above the divide button here. I've shown NCR here in greater detail in the exploded view of those 4 buttons, and to get NCR as an operation, you have to use the Shift key. So this sequence of keystrokes calculates 20C9. 20 shift divide 9 equals. And that produces the number 167,960. We can also calculate 20C9 directly from the formula for NCR and by using a calculator as the numbers become rather large. NCR equals n factorial over r factorial times n minus r factorial. So 20C9 equals 20 factorial over 9 factorial times 20 minus 9 factorial, which is 20 factorial over 9 factorial times 11 factorial. And after using the calculator to compute those factorials and the fraction, we obtain 167,960, as we did previously. On the same Casio calculator, we have an x factorial function, which is here above the x to the minus 1 button, and we get to x factorial using the Shift key. So to calculate 11 factorial, we use the key sequence 11 shift x to the minus 1 equals. Problem 2. Find the coefficient of the 5th term in the expansion of 2x plus 3y to the power 10. The rth term, t sub r, in the expansion of 2x plus 3y to the 10 has the form 10 choose r, 2x to the power of 10 minus r, times 3y to the power r, where r runs from 0 to 10 inclusive. So the 5th term of the expansion is t sub 4, the first being t sub 0, and t sub 4 is 10 choose 4 times 2x to the 10 minus 4 times 3y to the 4, which simplifies to 10 choose 4, 2x to the 6, 3y to the 4. By the rules of powers, that turns into 10 choose 4, 2 to the 6, x to the 6, 3 to the 4, y to the 4. And rearranging that, we get 10 choose 4, 2 to the 6, 3 to the 4, times x to the 6, y to the 4. Now the question requires that we find the coefficient of the 5th term. That means what we have to find is the number in front of the x to the 6, y to the 4, which is all of this part, all the numeric terms there shaded in red. And so the coefficient of the fifth term is 10 choose 4 times 2 to the 6 times 3 to the 4, which we can compute on a calculator to get 1,088,640. Problem 3. Find the term containing b cubed in the expansion of 3a minus 2b to the power 12. The rth term, t sub r, has the form 12 choose r times 3a to the power 12 minus r times minus 2b to the power r, where r runs from 0 to 12 inclusive. Now we require the term containing b cubed, so we must take r equal to 3. We therefore require t sub 3, which is 12 choose 3 times 3a to the 12 minus 3, which is 9, times minus 2b to the 3, which becomes 12 choose 3 times 3 to the 9a to the 9 times minus 2 to the 3 times b to the 3. And bringing together the numeric terms and the algebraic terms, the numeric part we can compute on a calculator to get this large number, minus 34642080, multiplied by a to the 9 times b to the 3. Problem 4. Use the definition of n choose r to show that n choose 0 equals 1 and n choose n equals 1 for all n greater than or equal to 0. Now, the definition, or at least the formula for n choose r, is n factorial over r factorial times n minus r factorial. And we are interested in n greater than or equal to 0, so we have to consider n equal to 0. And it's important to remember that we define 0 factorial to be 1. So first, considering the case where n equals 0, we have n choose 0 equals 0 choose 0, since n equals 0, which from the definition becomes 0 factorial over 0 factorial times 0 minus 0 factorial, which is 0 factorial over 0 factorial times 0 factorial. And recalling this fact, 0 factorial equals 1, we obtain 1 over 1 times 1, which equals 1 as required. And now, considering all of the cases where n is greater than 0, we have n choose 0 equals n factorial over 0 factorial times n minus 0 factorial, which becomes n factorial over 0 factorial times n factorial. 0 factorial is 1, so we obtain n factorial over 1 times n factorial, which is n factorial over n factorial, which is 1, again as required. So that shows that n choose 0 equals 1 for all n greater than or equal to 0. We now have to show that n choose n equals 1 for all n greater than or equal to 0. But if we first consider the case where n equals 0, then n choose n becomes 0 choose 0, which we have already shown here to be equal to 1. So we're done for the case n equals 0 already. Now, for the cases where n is greater than 0, we have n choose n from the definition is n factorial over n factorial times n minus n factorial, which becomes n factorial over n factorial times 0 factorial. We've seen this before. It becomes n factorial over n factorial times 1, which is n factorial over n factorial, which equals 1, as required. And so we've shown that n choose 0 equals n choose n, and they both equal 1 for n greater than or equal to 0. And we can see the significance of those facts by looking at Pascal's triangle. First of all, at the peak of the triangle, we have 0 choose 0, which is 1. Down this diagonal, we have 1 choose 0, 2 choose 0, 3 choose 0, 4 choose 0, and so on. And they correspond to the cases n choose 0 where n is greater than 0, and we can see that they are all 1. And then down this diagonal, we have 1 choose 1, 2 choose 2, 3 choose 3, 4 choose 4. They correspond to the cases n choose n, where n is greater than 0, and we can see that they are all 1, as we have already shown algebraically. Problem 5. Show that n choose r plus n choose r plus 1 equals n plus 1 choose r plus 1 for r greater than or equal to 0 and less than or equal to n minus 1. The relationship that we are asked to prove in this question is the algebraic representation of the left-right addition process for generating elements of Pascal's triangle. So here I've shown Pascal's triangle with the elements annotated with their n value and their r value. So for example, 3 choose 2 is 3 and 6 choose 4 is 15. And we generate elements in this triangle by adding elements in the previous row. So, for example, 10 is 6 plus 4. Or alternatively, 4 choose 2 plus 4 choose 3 is 5 choose 3. Or 5 plus 10 is 15. Alternatively, 5 choose 1 plus 5 choose 2 is 6 choose 2. And that process is what this relationship represents. And so, for example, the relationship shown here in this blue box, which is 5 choose 1 plus 5 choose 2 equals 6 choose 2, is what we get if we take this general relationship, which we have to prove, with n equals 5 and r equals 1. And by looking at Pascal's triangle, we can see why we require this restriction on r. If we set n equal to 5 and r equal to 5, we would be trying to prove that 5 choose 5 plus 5 choose 6 equals 6 choose 6, which corresponds to this part of Pascal's triangle. But we can see that the left-right addition process does not work here. We can take 5 choose 5, but we have nothing to add it to. 5 choose 6 is undefined and is not present in Pascal's triangle. So this restriction tells us that we cannot generate these values on this diagonal by using the relationship that we have to prove. We've noted that r ranges from 0 to n minus 1. The definition for n choose r, which can also be written like this, ncr, is n factorial over r factorial times n minus r factorial, and we will use that definition to prove this relationship. But note that n factorial has two different definitions, or there are two parts to its definition. If n is 0, then 0 factorial is defined to be 1. Otherwise, it's defined to be this product from n down to 1, all of the integers multiplied together. We'll note also that n factorial can be written as n times n minus 1 factorial, because this part of the definition, n minus 1 times n minus 2 down to 3 times 2 times 1, is in fact n minus 1 factorial. Now, since n factorial has two different definitions depending on whether n is or is not 0, it's convenient to prove this relationship for the cases r equals 0 and r not equal to 0. And the procedure that we shall follow will be to show that the left-hand side of the relationship can be rewritten in the same form as the right-hand side of the relationship. And so for the case r equals 0, the left-hand side becomes n choose 0 plus n choose 0 plus 1, which reduces to n choose 0 plus n choose 1, We then apply this definition to turn n choose 0 into n factorial over 0 factorial times n minus 0 factorial, and n choose 1 into n factorial over 1 factorial times n minus 1 factorial. This term reduces to n factorial over 1 times n factorial, since 0 factorial equals 1. This term turns into n factorial over 1 times n minus 1 factorial. Now, all of this simplifies to 1, since the n factorials divide away, and we are left with 1 plus n factorial over n minus 1 factorial. And now we note that n factorial can be written as n times n minus 1 factorial to turn n over n minus 1 factorial into n times n minus 1 factorial over n minus 1 factorial. These terms cancel, the n minus 1 factorials, to leave us with 1 plus n, or as I would prefer to write it, n plus 1. And so the left-hand side, in the case r equals 0, reduces to n plus 1. For the case r equals 0, the right-hand side is n plus 1 choose 0 plus 1, which is n plus 1 choose 1. Applying the definition for n choose r, we get n plus 1 factorial over 1 factorial times n plus 1 minus 1, all factorial. The bottom of this fraction reduces to n factorial, since 1 factorial is 1 and n plus 1 minus 1 is n. We then factorize n plus 1 factorial as n plus 1 times n factorial. We have n factorial on the bottom, n factorial and n factorial cancel to leave us n plus 1. And so in the case r equals 0, the left-hand side reduces to r plus 1, the right-hand side reduces to r plus 1, so the left-hand side equals the right-hand side as required. So this relationship is true when r equals 0. And note that the substitution I made here, going from n plus 1 factorial to n plus 1 times n factorial, comes from the relationship n factorial equals n times n minus 1 factorial, which turns into n plus 1 factorial equals n plus 1 times n factorial if we make the substitution n goes to n plus 1 in the first relationship. We now deal with the cases where r is not equal to 0, which is all of the rest of them, and we follow the same procedure. We show that the left-hand side can be rewritten in the same form as the right-hand side, and recall that this is the relationship that we are trying to show. Now in this case, it's worth writing out the left-hand side and the right-hand side and comparing them. The left-hand side, when we apply the definition of NCR to n choose r plus n choose r plus 1, becomes this somewhat complex thing. The right-hand side, n plus 1 choose r plus 1, becomes this expression, which reduces to this somewhat simpler expression. And we can see that this is the more complex expression, the left-hand side. This is the simpler expression. And generally, it is best to try to turn the more complex expression into the simpler expression. Before we start with the details, let's note these two relationships which we will use. Firstly, n plus 1 factorial equals n plus 1 times n factorial, and n minus r factorial equals n minus r times n minus r plus 1, all factorial. And it's worth noticing the following pattern in both of these factorizations. We turn n plus 1 into n by subtracting 1. We turn n minus r into n minus r plus 1 by subtracting 1. And so we start with this expression for n choose r plus n choose r plus 1, and we wish to show that it can be rewritten in this form, which is n plus 1 choose r plus 1. And first note that we can factorize n minus r factorial as n minus r times n minus r plus 1 factorial, and we can factorize r plus 1 factorial as r plus 1 times r factorial. And now we can note that we have a number of common factors in the two fractions: n factorial, r factorial, n minus r plus 1 factorial, n minus r plus 1 factorial. And we can pull out those common factors, as I have done here, to leave behind in brackets 1 over n minus r plus 1 over r plus 1. And we can combine these terms into a single fraction with a common denominator of n minus r times r plus 1 and a numerator of n minus r plus 1, where we can see that the minus r and plus r cancel. And so inside the brackets, we are left with the fraction n plus 1 over n minus r times r plus 1. And now we're done, because we note that n plus 1 times n factorial is n plus 1 factorial. N minus r times n minus r plus 1 factorial is n minus r factorial, and r plus 1 times r factorial is r plus 1 factorial. But that, of course, is precisely the expression that we had to produce to show that both sides are equal. Problem 6. By considering the expansions of x plus y to the power n and y plus x to the power n, show that the binomial coefficients in any row of Pascal's triangle are palindromic, i.e. that n choose r equals n choose n minus r. First, we need to understand what this question is asking us to show. We need to know, what does palindromic mean? Well, a palindromic word is one that reads the same forwards as backwards. And so, aha, madam, and indeed this phrase, able I was ere saw I Elba, all are palindromic. In addition, the digits in the number 121, which are 1, 2, and 1, reading forwards, and 1, 2, and 1 reading backwards, form a palindromic sequence. And so, in fact, perhaps this question should have said, show that the binomial coefficients form a palindromic sequence. And if we look at the rows of Pascal's triangle, we can see that they do indeed form palindromic sequences. For x plus y to the 1, we have 1, 1 forwards, 1, 1 backwards. X plus y to the 3, 1, 3, 3, 1 forwards, 1, 3, 3, 1 backwards. X plus y to the 6, 1, 6, 15, 20, 15, 6, 1 forwards, 1, 6, 15, 20, 15, 6, 1, reading backwards. Now, the values 15 and 15 in the row for x plus y to the 6 correspond to 6 choose 2 and 6 choose 4. And so we can see that 6 choose 2 equals 6 choose 4, but 4 equals 6 minus 2. So 6 choose 2 equals 6 choose 6 minus 2, which is a specific example of this general relationship which we have to prove. Now, we have to solve this problem by considering the expansions of x plus y to the power n and y plus x to the power n. First, let's look at the expansions of x plus y cubed, which I've shown here, and y plus x cubed, which I've shown here. Now, the first thing that we should note is what I've shown in this rectangle here, We know that x plus y equals y plus x for any real numbers x and y. So x plus y to the n must equal y plus x to the n for any integral value of n. And so in particular, when n equals 3, x plus y cubed must equal y plus x cubed for all values of x and y. And of course, that implies that the right-hand sides of these two expansions must also be equal. Now, note that we can turn the expansion for x plus y cubed into that of y plus x cubed by swapping the roles of x and y, by replacing x with y and y with x wherever they appear. So, for example, the first term, 3 choose 1 x squared y, turns into 3 choose 1 y squared x. And now note that if we look at the second term in the expansion of x plus y cubed, we have an x squared y expression, and in the third term of y plus x cubed, we have a y x squared term. Of course, yx squared equals x squared y. So we must have that this term equals this term, and consequently, we can write down this equation, 3 choose 1 x squared y equals 3 choose 2 yx squared, and then, by the process of equating coefficients, we can say that 3 choose 1 must equal 3 choose 2. And now we can play the same trick with the general expansion of x plus y to the power n. We know that x plus y to the power n equals y plus x to the power n, so the left-hand side of these two equations are equal, and consequently the right-hand side of these equations are equal. Now let's look at the terms containing x to the n minus r, y to the r in both the top equation and the bottom equation. Those two terms must be equal for all values of x and y. So this term must equal this term, and consequently we can write the equation written here, n choose r times x to the n minus r times y to the r equals n choose n minus r times y to the r times x to the n minus r. And by equating coefficients, we have n choose r equals n choose n minus r as required. And we're done. Problem 7. Use the definition of NCR to show that the binomial coefficients in any row of Pascal's triangle are palindromic, i.e. that n choose r equals n choose n minus r. This problem is in fact identical to problem 6, except here we have to use the definition of NCR to show this relationship. The definition of NCR is given by this equation. NCR equals n factorial over r factorial times n minus r factorial. Now, by making the substitution r goes to n minus r in this equation, we can see that n choose n minus r becomes this more complex expression. And so to prove this relationship, we have to show that this expression is the same as this expression. But in fact, this relationship is rather easy to prove. We have n choose r equals n factorial over r factorial times n minus r factorial. By making the substitution r goes to n minus r, we turn n choose r into n choose n minus r. Doing the same thing on the right-hand side of that equation, r goes to n minus r, turns n factorial over r factorial into n minus r factorial into this expression, which is n factorial over n minus r factorial times n minus r factorial, which becomes n factorial over n minus r factorial times n minus n plus r factorial. the n's cancel to give us n factorial over n minus r factorial times r factorial, which we can write as n factorial over r factorial times n minus r factorial, which is precisely n choose r. So we are done. Problem 8. By choosing suitable values for x and y in the expansion of x plus y to the power n, show that a. the sum of the binomial coefficients equals 2 to the power n, b. that the sum of the even binomial coefficients equals the sum of the odd binomial coefficients. The expansion of x plus y to the n is given by this expression. And for part A, we can see that if we can make x plus y to the n equal to 2 to the n by choosing suitable values for x and y, we will have solved the problem. But we can do that very easily, since if we let x equal 1, y equal 1, then x plus y to the n equals 1 plus 1 to the n, which equals 2 to the n. And then substituting those values in this right-hand side expression, we obtain 2 to the n equals this expression with the x's and y's all replaced by 1 wherever they occur, and we get terms of the form, say, n choose 2, 1 to the n minus 2 times 1 squared. The 1 to any power term turns into 1, and we are left with the expression we desire. N choose 0 plus n choose 1 plus n choose 2, and so on, all the way up to plus n choose n minus 2 plus n choose n minus 1 plus n choose n. And for part B, we can play a similar trick. Let x equal 1, y equal minus 1. Then x plus y to the n is 1 minus 1 to the n, which is 0 to the n, which is 0. Now here, I've written out the first 6 terms of the expansion of x plus y to the n. And we can note that these terms have even powers of y, and these terms have odd powers of y. On substituting these values of x and y into this expression, we obtain this, and we see that the terms with odd powers of y will produce minus 1, because minus 1 to an odd power is minus 1. The x terms all produce 1. And consequently, the whole expression simplifies to this, which has alternating positive and negative terms, each of which only contains a binomial coefficient. The odd terms, n choose 1, n choose 3, n choose 5, become negative. The others are positive. And note that since the whole expression equals 0, we can add the negative terms to both sides to give us the desired result. The sum of the even binomial coefficients equals the sum of the odd binomial coefficients in the expansion of x plus y to the power n.